So there are a few prerequisite things that you really should know before embarking on this journey with me. Alright, first thing is you should know what a set is. You should know what the cardinality of a set is. You should know what a power set is. A proper subset versus just a set, right? You should know what intersections and unions of sets are. You don't have to have some advanced topology knowledge of these notions, just understand what they mean and how to manipulate them, like with De Morgan's laws. You should understand basic logic, again with the De Morgan's laws thing. You should understand things like and or, exclusive or, right? You should understand what a truth table is. You should understand what I mean by the term function or mapping, right? That if we have two sets and I say f s to t is a mapping between sets, you should know what it means, and you should know what a surjective mapping is, what an injective mapping is, what a bijective mapping is. You should know what an equivalence relation is, right? And the three axioms of equivalence relations. You're going to want to know what a binary operation is. And if you've gotten this far and you understand all of this thoroughly, but a binary operation maybe is a new concept to you, then I will just say this. A binary operation is a function from a Cartesian product of two sets, so S cross itself usually, to that set, right? So it takes two elements from a set in and spits one element from that same set out. And that's really all it is, right? So you take A star B, we could call it star if you want, or you could call it plus or times or divide or whatever you want to, whatever symbol you want to use, right? A binary operation is just a function from the Cartesian product of a set with itself to that set. And of course, normal addition for, say, integers, this would be z cross z to z. A times b for, say, real numbers would be a function from r cross r to r. And this is pretty much all there is to it. Any properties that are beyond this of a binary operation we will cover. We need to know that P implies Q is the same as not Q implies not P, right? And how to use the contrapositive as a proof technique. We need to understand what direct proof means, what proof by contradiction means, what proof by mathematical induction means, and it wouldn't hurt to have some problem-solving techniques under your belt like the pigeonhole principle or other, just general ideas, although those aren't strictly necessary. So first I want to talk about why we study group theory. Why introduce such abstract concepts and enter into this world of the imagination as it's going to seem at first? In the first place, I mean, why not just talk about things concretely? So, let me give you a few examples. Suppose we want to study the symmetries of an equilateral triangle. So we have all the same lengths here and all the same angles here. We want to study the symmetries of this geometric object. What do I mean by that? I mean, we want to look at all the reflections, all the lines of reflection, to where if you reflect it, you get the same shape back. So you're going to get these three lines of reflection. And then in addition to reflection, you have rotation, right? Rotation by 120 degrees, or pi over, or 2 pi over 3, radians. Now suppose we call a rotation by 120 degrees counterclockwise, we'll call that r. And then we'll call r squared the application of r 2 times successfully equals r, then r, right? And we'll call a successive operation on this just multiplication. We'll denote that by multiplication. So that you get r cubed is going to be 3 rotations by 120 degrees. And what are you going to get? You're going to get nothing in return. Because if this goes all the way around to here, and then a second time, and then a third time, then you notice it's going to be in the exact same position as it was to begin with. So we want to encode this as being nothing, if you will. We'll call it the identity operation on this. And then another thing we want to do is encode these reflections. So suppose we have, we'll call our 3 reflections, just for sake of argument, we'll call reflection about this axis, we'll call it L sub A, is going to be the element A, multiplication by A, if you will. Reflection about this axis, LB, and this axis, LC, similarly, we're going to have A, B, and C are our 3 reflections. Okay, and we notice that if you apply any reflection twice successively, this is also going to be equivalent to doing nothing. So b squared is equal to I, c squared is equal to I. And then what we're really interested in is talking about all possible combinations of these things. Can we classify all of them? Well, yes, we can, right? Because any of these rotations, say we rotate by 120 degrees, we can actually encode that as 2 reflections. All right, suppose now that I look at what happens to this point as I reflect over here. So if I reflect over L sub A, so I do the operation A, then I get this point here and this point here, but this point stays unchanged. And then suppose I follow that by rotation, reflection about, say, line C. So I do, if you will, A times C. Or actually, C times A is the way I'm going to write this. Doesn't matter right now, the details. But so this point is going to go to this point, and then where's it going to go? So if we label these 1, 2, 3, we're going to have 1 going to 2, and 2 going to 1, and 3 going to 3. That's going to be our first operation. And then our second operation is whatever's in position 2 is going to go into position 3. So 2 to 3, 3 to 2, and then it's going to keep 1 the same. So if you follow these up back to back, you get 1 goes to 2, 2 goes to 3, so that 1 goes to 3, 2 goes to 1, 1 goes to 1, so 2 goes to 1, and 3 goes to 3, and then 3 goes to 2, so that 3 goes to 2 in the end, right? This is the composition, if you will, of the 2 actions. A reflection across line A, followed by a reflection across line C. All right. But now look at this. 1 goes to 3, 3 goes to 2, 2 goes to 1. What is this? This is just a rotation in the clockwise direction by 120 degrees. So that we notice that C times A is equal to, if you like, the inverse element of R. And I haven't explained what an inverse is, but you could just think of it, if a rotation by 120 degrees counterclockwise is our R, then it makes sense to call R inverse the rotation by 120 degrees clockwise, right? And likewise, if you did AC instead, you would get R. But R inverse could also be written as, well, let's just keep it like that. So what we notice is that there's these sort of algebraic ways to encode what's going on with the symmetries of this polygon, and this is a really cool thing. So maybe that if we could figure out some symbols and how these symbols manipulate with representation, as a representation of this polygon, then maybe we could completely classify everything that's going on with a polygon. Likewise, maybe for more complicated shapes, it might actually be simpler to look at this sort of algebraic angle. So we already see that there's a way to use algebra, if you will, to encode symmetry. This is what group theory is all about. And group theory is at the heart of modern mathematics. But it doesn't require a lot of prerequisites, which is really nice. It just requires a willingness to get your hands dirty and abstract stuff. Now, another motivation we have is that we notice that various number systems have a lot of the same common properties. What do I mean by that? I mean that if we have two real numbers, x and y, then x plus y is equal to y plus x. Now, this isn't anything particularly special, you're thinking, but this is not true for all objects, right? It's not true that you can, if you define some operation between two things, that it need to have this symmetry. And once again, we have another concept of symmetry here. Now, you might have learned this as the commutative property in, say, high school algebra or something like that. Or maybe elementary school algebra, I don't know where they teach this now. But, okay, so that has a name. And we notice that it also holds for complex numbers, right? So if you had x plus iy plus, you know, a plus bi, this is the same as a plus bi plus x plus iy, right? Where I is the square root of -1. So they both obey the commutative property. Now, likewise, there's another type of commutative property that shows up with multiplication. So a times b, if we have two numbers a and b, a times b is usually equal to b times a. For instance, 5 times 4 is, you know, 5 groups of 4 objects is 20 objects, is the same as 4 groups of 5 objects, right? Which is also 20 objects, if that's the way you want to think about multiplication. So we also have this sort of symmetry thing going on with multiplication. So maybe this is more than just about one particular number system, or maybe even any number system. This is what algebra is all about, starting from first principles with operations on sets, and then using various properties of those operations on those sets to deduce facts. And then these facts turn out to be the encoding of symmetry. These theorems describe all kinds of symmetries. Any kind of symmetry you can imagine in the world can be described by algebra, by symbols and formal rules of manipulation. And this is all what group theory is all about. So by studying groups, we can study the properties of numbers, the properties of reflections and rotations and geometric objects, and many other things all at the same time, just by boiling it down to a few rules and definitions, and then logical deductions from those.